The second algorithm I'm going to run for you is the A* search algorithm. This is also going to return for me the optimal path, but the theory is that it should do a little less work, or even a lot less work, due to the fact that it's going to use a heuristic to do an informed version of the search. Let's have a look at how this works. As you can see in the search space now, each node in the search space has a number next to it, and that number is an estimate, a quick to compute estimate of what the cost is between that state and one of the goal states. So the estimate is that between node D and one of the goals, it's going to cost 6. As you can see, the actual cost of the shortest path between D and a goal state is actually 9. So this is an underestimate, and this turns out to be important. In order for the A* search algorithm to return the shortest path, you must use a heuristic that never overestimates the cost. So either it underestimates or it gets it entirely correct. So here I've got heuristic values that are never overestimating the cost, and therefore what that means is that A* is going to return the optimal path for us. Let's see how this works. It works in a similar way to uniform cost search, except that we use the A* score. That's the cost of the path so far, as we used in uniform cost search, plus we add onto that the heuristic of the end node of the path. So that gives you an estimate of the total cost of the path that you're looking at so far. Let's see how this goes here. We look at this, it's not the goal state, so we're going to expand it. We'll add it to the visited list, and we'll also store its A* score, so that we know it's A* score. If we find a better one than that, then we know that we need to visit it, and this can happen in the A* search algorithm. Let's expand it. So we can go to A, to B, and to D for a cost of 5, 9, and 6. We have to take the heuristic measure into account as well. The heuristic measure for A is 7, so the algorithm thinks it's going to take 7 units of cost to get from A to the goal state. From B, the heuristic measure is 3, and from D, the heuristic measure is 6. So the A* score is the cost of the path so far, so that for this one that's 5, plus the cost of the heuristic measure, so that's an estimate of how far it's still to go to get to the goal state, and that gives you an estimate of what the total cost of this path is going to be once it's actually got down to a goal state. So it's 12 here, 9 plus 3, it's 12 for this path as well, and 6 plus 6, it's also 12 for this path. So at the moment, the A* search is not distinguishing between these possibilities. It thinks that each of these paths is going to cost 12 in the end. So let's just take them in alphabetical order as we did before. We'll look at this one first. From A, we can go to B or we can go to G1. So let's put those up there, B and G1. The heuristic measure for B is 3, and the heuristic measure for G1 is 0 because it's a goal state. And the heuristic measure can understand that G1 is a goal state, and therefore it doesn't cost any units in order to get to a goal state from there. From A to B, that's a cost of 3. From A to G1 is a cost of 9. So we now calculate the A* scores. So the total cost of the path along here is 8, 5 plus 3. We then add in the further 3 here, and that gets us to 11. So the total estimated cost of that path is 11, the 8 plus another 3. And for this path, it's 5 plus 9, which is 14, plus the 0, and that takes us to 14. And we now mark A as visited and add it to the visited list with an A star score of 12. If later on in the search we find a path to A that has an A star score of less than 12, then we will look at that. However, if we find later on in the algorithm a path to A with an A star score of more than 12, then we can completely ignore it and prune that part of the search. Okay, so we now continue. We've got 4 active paths in the tree, and the one with the best A star score is this one here, ending in node B. So we look at node B. From node B, we can go to A for a cost of 2, or we can go to C for 3. Now, if we went to A for a cost of 2, then the total A star score of the path leading to A here would in fact be 20, 13 plus 7. So we've already visited it for 12, we don't need to add it back to the tree. But for the other node, B to C, we will add that to the tree. So C has a heuristic cost of 4, that's the estimate of how far it is to a goal state, and its cost of 1 to get there. So it's now 9 along that path, plus the 4, which makes it 13. And that one has now been visited, so B has now been visited, and its A star score for the visit was 11. We've now got 4 paths in the tree, 1 for 13, 1 for 14, and 2 for 12. So we're going to take one of these 2, we'll just take B first. Well, B has already been visited for an A star score of 11 over here, so there's no point in visiting it for an A star score of 12, so that's a dead end. Now look at D. From D we can go back to S, we can go to C and to E. The route back to S is not going to be visited because we've already visited that for an A star score of 5. However, we can add in C and we can add in E. The cost is 2 in each case. C has a heuristic value of 4. E has a heuristic value of 5. Let's calculate the A star scores. So it's 8 plus 4, that's 12 along that path. And along this path here it's 6 plus 2, that's 8, plus 5, which brings us to 13 along this path. We now add that to our visited list, so D has been visited for an A star score of 12. Let's look at the remaining active paths in the tree. Well, we've got this one for 13, this one for 14, here's one for 12 ending in C, and here's one for 13 ending in E. So it's going to be this one that gets explored next, the one ending in E for an A star score of 12. That's one ending in C for an A star score of 12 rather. So let's look where we can go to from C. Well, we can go back to S, but we're not going to do that because its A star score when we visited it was 5, and it's going to be more if we visit it this time. But we can go to G2 and we can go to F. So let's put those into the tree. To G2, that has a heuristic score of 0 and the cost of the arc is 5. And to F, F has a heuristic score, a heuristic estimate of 6, and the cost of the arc is 7. So let's calculate the new A star scores along these new branches. So it's 8 plus 5 plus 0 is 13. And 8 plus 7 is 15. 15 and 6 is 21 for that branch there. So that's our most expensive branch so far. Give C a tick and add it to the visited list. So C has been visited for a cost of 12. Let's look at the remaining branches. Well, we've got C here for an A star score 13, G1, A star score 14, G2 for an A star score 13, F for A star score of 21 and E for 13. We've got 3 that end in a 13, 3 that have a score of 13. We're just going to take them in alphabetical order. So we'll visit this one first, C for a score of 13, but we already visited C for an A star score of 12. It's in there, so there's no point in expanding that node. That's a dead end. Then we go to E for the next one. E, we can go to G3 for a cost of 7. G3 here. We calculate the A star score of this new path. So that's 6 plus 2, that's 8. Plus 7 is 15. 15 and 0 is 15 for this branch. E has now been visited for an A star score of 13. And at this point, we've now got 1, 2, 3, 4 active branches. 14, 13, 21 and 15. So this is the best one. We look at the node to see if it's a goal state, and it is. So we have now reached the goal, and because the heuristic that we used was an admissible heuristic, we know that this path here is the optimal path through the tree. And I'll mark that for you in red as before. What we noticed was that the algorithm, the A star algorithm here, has done a fair amount of work. It's visited a fair number of nodes and it's expanded quite a lot of the tree. The reason for this is that the heuristic measure that we used in the search space wasn't very accurate. So for example, the heuristic is estimating that it costs 5 to get from S to a goal state, and we now know that the actual cost is 13. So what I'm going to ask you to do for the assignment is that I'm going to ask you to run the search, the A star search again, but I'm going to give you more accurate measures for the heuristics from each of the node to see what difference that makes.